Welcome to the course Business Analytics and Text Mining Modeling using Python. So, in previous few lectures we have been discussing some of the steps that are required to process the text, convert transform the unstructured text into a form where we can do our text mining modeling. So, specifically we were talking about expanding contractions. So, we talked about that aspect, we talked about the mapping contraction mapping that we discussed in the previous lecture. So, let us go through quickly briefly this and then we will continue. Here we are defining a function that can be used to expand contractions in the text. So, you can see define expand underscore contractions and any sentence text and then mapping. So, mapping that we discussed before, we have a dict object there. So, we can use that to perform our mapping here. So, here we are again using pattern for matching contractions with their expansion. So, you can see that this pattern here, and will be using this pattern to actually find out all the contractions with their expansions for a sentence. So, you can look at this part of the code. So, here I am calling this using the pattern dot sub. I am finding out all the occurrences here expand underscore map, and this particular this function is being called, which will actually essentially it will do the mapping. So, this part we have discussed in the previous lecture. So, this is the function that we defined to perform this. Now, once we through this, then we can apply this expand underscore contraction in one of the text. So, I have taken this sample text here. You can see the young man wasn't fast enough and he couldn't win the race. So, wasn't and couldn't are the two contractions that are there, and let us use our function and let us see whether they are converted into their expansion form. So, let me run this, and you can see in the output that wasn't has been converted into was not, and couldn't has has been converted into could not. So, you can see the function is working quite well. Now, the same thing we can apply in our this text document, that is Emma file that we have. So, we can use this user defined expand underscore contraction function on clean text Emma underscore f that we had cleaned in previous lectures. So, if I run this, and you can see now we have Emma underscore fe after this expansion process, and if we will have a look at the first 500 sentences here. So, many places you would be if you compare this output with the Emma sentence output, then you would be able to identify that many places where contractions were present, now they have been mapped to expansions. So, in this fashion, in one go we can actually perform this. Now, let us move to the next aspect, that is case convergence. So, sometimes we might require certain case convergence to be performed. So, for that we can just take the we have taken this example. If we want lower cases, so we can type like this Emma underscore sends and 0 just for an example send first sentence and dot lower. So, we are calling this lower method, and it will convert all the text into lower case. If I run this, we will have this converted into lower case. This is, so you can compare. Similarly, for upper also, similarly you can see all the text can be converted into the upper case as well. Let us move forward. Now, we will talk about another aspect, that is removing stop words. So, what we mean by stop words, essentially it is about the terms like a, the or the, me. So, these words which are not really meaningful in the text analytics context, in the text classification context. So, we might prefer to remove these terms, and because we would like to later on, as we will discuss, we will like to identify relevant features, relevant vectors which will help us in our text classification problems. So, therefore, some of these stop words which are not going to add much in that context, we would like to get rid of these terms. So, stop words again these are language and domain dependent. So, depending on the language, English typically these stop words differ from language to language, and also domain. So, certain domains, certain words might be meaningful, and certain another domain they might lose importance there. So, however, we do not have any universal or exhaustive list in this case. Still we have for English language we will use this NLTK module where we have a list of stop words. So, that we will be using to get rid of these words from our corpus. So, typically removing stop words after tokenization because it makes the process slightly easier for us. So, we will talk about writing a function to filter stop words from tokens. You can see now we are defining the function def remove underscore stop words tokens. We will be passing tokens here, and then we will use English language stop words here. So, you can see we are creating this sequence underscore SW, this list of the stop words, nltk.corpus.stopwords.words and English. So, we will have the list here, and then we are running this list comprehension tokens underscore f. So, we are filtering these stop words. So, that is why underscore f. So, tn so here you can see tn for tn in tokens if tn not in sequence underscore sw. So, if a particular token is not already present in the list of stop words, then we will have that in our filtered tokens list. So, this is the function. So, if I run this, and now we can apply this particular function in our emma underscore words. So, we will be using this user defined remove underscore stop word function on tokens. Remove underscore stop words emma underscore words, these tokens we have already created. So, if I run this, we will have emma underscore words underscore fs. Let us have a look, and in the output if I scroll through this, you can see if you look at Emma, Jane, Austin 1816, and you would see that all the stop words A and the kind of terms are gone. So, if I scroll through this, you would see only meaningful words have remained, and so all others are gone. So, let us have a look at the number of tokens after removal process. So, we can use this len function, and you can see the number of words after this stop word removal process. We have 1,12,632, and if we look at the original list here, so you can see 1,91,000. So, approximately about 80,000 words we have lost just by removing stop words. This is the reduction in size that we have been able to perform. Now, if you are interested in having a look at the list of all English stop words, you can again print this list nltk.corpus.stopwords.words English. If I run this and if I go back to the output, you can see these could be some of the stop words. These are some of the listed stop words for English language. You can see I, me, my, myself, we, our, ours. So, these are some of the words which might not be meaningful for our text analytics context or text classification problems. So, these are the stop words that we typically would like to remove. So, the same thing I mentioned in the comment part also. So, however, there might be certain exceptions also. For example, negations like not and no, they might be important sometimes, specifically if we are doing sentiment analysis. So, there sentiment analysis will also involve will have negation aspect. So, therefore, these words might become important there. So, we will have to really see whether we can really remove these stop words, whether we can afford no and not in these stop words. So, if I just scroll through, we might encounter. However, if that is the case, you can see here no nor not here. So, they are right now in the stop words, but if we are performing sentiment analysis, probably will be better off not removing stop words, because we might lose no or not, or we can prepare our own list, own stop word list. Let us move forward. So, another aspect that we might encounter in processing text, in transforming text, is correcting words. So, there could be spelling mistakes, there could be repeated characters sometimes. Especially informal writing, if somebody is writing in a social media platform or in the comment section of e-commerce website, they might write, to emphasize certain words, they might repeat certain characters. So for our text analytics purpose, if we want to remove those if we want to correct those words, so how we can perform that? So let's talk about this. So we'll pick up the repeated characters scenario. So here we'll be using a regex pattern and different match groups 1 2 3. So if pattern like R within single quote /1 /2 /3, this is essentially we can use different groups in a pattern and reconstruct another pattern. That this would be really useful for us in repeated character scenario. So let's have a look at the function here. Now here it will also be important for us to check check for valid words. So for many of these words, for example repeated character, for example finally, and there we have y repeating many times or l repeating many times. So where do we stop while we are trying to remove some of those repeated characters? So for that we'll have to take the help of WordNet corpus to actually check whether in that removal process whether we have reached a valid word case. So that will have to perform here. So let's have a look at the definition of this function. Remove underscore repeated underscore characters. So we are passing tokens here. So now will be in the pattern that we are going to use here is this characters that occur twice among other characters. So if you look at the pattern, we have used parentheses to identify different groups here, and you can see the second group this is /2 indicating that occurring twice. Now these are back references. So we'll be using back references to construct the replacement for the pattern. So one thing is to match a particular these kind of repeat words with repeating characters. The another thing is to replace them or eliminate the repeating characters. So here when we say /1, so /1 will be replaced with the substring matched by group 1 in the pattern. So /1 is actually a back reference to the group 1, /2 is a back reference to the group 2. So when in the first line pattern re.compile, where you can see /2, it is actually referring to, it is a back reference to group 2, which is nothing but /w. So the same word is repeating here. So that is why in the comment section we say characters that occur twice. So in this fashion we have defined the pattern that will be used for matching, and then for the replacement. So if you look at the pattern that we are using for replacement, we keep one instance of the repeating character in group 2. So you can see REPL, this is our replacement pattern, or within single quotes /1, that is group 1, then /2, that means just one instance of that repeating character, and then /3. So /1 and /3, they are back references. The first and the third group, they are being kept intact, and /2 is just once, so just one occurrence we would like to keep here. So this is how the pattern will use to match, and replacement REPL will use to actually replace the matching occurrences. So now let's have a look at the code in a more detail. So if you come down to this part, correct each token. So here you can see we are using a list comprehension. We are calling replace function for tn in tokens. So for each token in the list of tokens that we might be passing, we will be calling this replace function here. So let's have a look at replace now. So once we receive a token, we'll check in the WordNet whether that is a syntactically correct word or not. So it might be so. So we would like to stop at that point of time. So if WordNet.synsets and within the parenthesis tkn token, then we will return token. If it is true, then we will return token. That means we have arrived at a syntactically correct word. If not, then we will like to replace the pattern. So tkn underscore c, and we are calling using this regex object pattern dot sub and REPL will be used to replace. So, all the matching occurrences of the pattern, they are going to be replaced with REPL in that particular token TKN. Now, then we are making a recursive call here. So, you can see if token underscore c is not equal to token, in that case we are again calling replace tkn underscore c, and if it happens to be if it happens to be equal to, then will return tkn underscore c itself. So, in this fashion recursively, because one character might be repeated many times. So, once we remove, let us say it is repeating 4 times. So, we removed once, then again we will we will check whether it is equal or not. If it is not equal, then again we will call replace, and in that fashion we will go on in this fashion till we arrive at a situation where in a recursive call the first if that we have wordnet dot syn sets, there we are able to reach the syntactically correct word. So, somewhere this return will help us reach the syntactically correct word, and that is the place where this if tkn underscore c not equal to token would actually become false, and the else part would be returned. So, it will end this recursive loop there. So, this is how this code will work to actually remove the repeated characters. So, let me run this, and let us take an example here. So, here you can see test 1, this is the sentence this we are taking. You can see all the words they are having repeated character, and then we are calling our we are tokenizing this sentence here. We are calling word underscore tokenize, then we are passing this token to our user function that we have just defined, remove underscore repeated characters. So, if I run this, and you can have a look at the output 81, you can see HM there is because we won't reach a syntactically correct word there. So, only will this function will be called, recursive call will keep on happening till we are left with just one M. In the second case, O triple H will be left with OH, because that is also again same example, it might not be syntactically correct word. Then third one, thanks, you can see there dot is repeating thrice. So, that is gone, and thanks is a syntactically correct word. So, it will stop there. Similarly, really you can see 2 y's and 2 l's are gone, because only then will be able to reach the syntactically correct word. Similarly, wow also, there also those in extra o's are gone. So, in this fashion our you can see that the function that we have just defined is working quite well in terms of removing repeated characters. Now, let us talk about let us apply this remove underscore repeated characters on emma underscore words underscore fs as well. So, let me run this, and if there are any such instances in this particular text corpus, then those would also be corrected, but because emma was part of formal writing, so I do not expect this to happen in that case, but anyway we can call this function. So, with this let us move on to the next aspect that is very important for text processing, that is stemming. So, what is stem or word or word stem? So, essentially what we mean by this process stemming is we would like to reach the base or root form of a word, because in there could be multiple variants of a root form of a word. For example, text, we might in writing we might have texts, texting, texted. So, we would like to just keep the root form of the word. So, essentially when we say stem or word stem, we are essentially referring to that particular root form of the word. So, this might this kind of processing, if we are able to perform this kind of stemming in our text corpus, it will really help in our text analytics and text classification context. We will talk this in more detail. So, Stemming can also be considered as reverse of inflection. So as we said, useful in classifying or clustering text, and even in sometimes in information retrieval. There are so many available NLTK interfaces for this. So we will talk about the first approach, which is Porter algorithm. This is the most popular approach. So in this one we perform phase wise rules. We use phase wise rules for reduction of inflection to their stems. So let's have a look at the code here. So for this we will have to import this from this nltk.stem module. We will have to import this this class porter stemmer, and then we will define an instance of this porter stemmer class, and let's run this. If you look at PSTM, you can see this is porter stemmer instance of porter stemmer class. Now we can call this stem method using this instance and pass on the pass on the examples here, for example text or texted or texting, and it will give us the root form of the word. So if I run this, you can see texted will get text, texting again will get text. Now if I take an example like flying, so if I run this, we get FLI, and for strangulate, if I run this, you can see strangle. So in this fashion you can see different forms of a word would be there in writing, in a would be there as part of a text. So how we can use stemming algorithms, for example in this case we use Porter's method. So how we can use these methods to actually arrive at a root form of the word, and what it will how it will help us in text analytics, in that sense that if in your text, if you have if you have words, if you have variants like text, texted, texting, and all of those instances would be converted into text. So therefore frequency of text will increase, and that will be really helpful in our vectorization steps, or later on when we apply machine learning algorithms. So because the frequency will increase, so and you would see that as we have talked about, that in our tabular layout we'll be counting the for a particular term, we'll be counting how many times it has appeared in a particular document. So that information is important. Now in this, if we perform stemming, so it will really help us in terms of having a fair distribution of root words or stems. So it will statistically it will help us in terms of distribution of words, and therefore application of machine learning algorithms will also be useful. Now let us talk about the second approach. This is Lancaster's stemmer. So this is iterative and follows rule based steps for removal or replacement of affixes to their stems. So when we talk about root form of a word or stem, so there are going to be affixes there, prefixes or suffixes, and different variants of that words would be there in the writing. So this particular algorithm is based on removal or replacement of these affixes. So let us import this Lancaster stemmer class, and we will be using an instance of this class. So let me run this, and you can have a look at the class Lancaster stemmer. This is an instance of that. Now we will be again calling stem method of this particular class, and we will be passing on the same examples, same words we will be using here again, and we will try to find out the root here. So you can see same output for texted, also same output for texting, also same output like Porter algorithm. Now we run it for flying. You can see we got fly here. In the Porters we got FLI. So you can see different different stemming algorithm. They might give you different output depending on what kind of steps they follow. If I run this strangulate on this, so for this I think it is the again there are also difference in terms of Porter algorithm. We got a strangle, here we got a strangulate itself. So, you can see these two different algorithms, they are working slightly differently when it comes to stemming. Now, let us move to another aspect, that is lemmatization. So, lemmatization is quite similar to stemming, and in stemming typically root or base form of a word that we typically obtain, that may not always be lexicographically correct word. So, we are just trying to arrive at a stem or root form of a word which might not be present in the dictionary in other words. But when we perform lemmatization, it is the root or base form of a word that will also be present in dictionary, that is taken. So, slight differences there. So, root form of or lemma is formed by removing the affixes from the word if and only if lemma is present in the dictionary. So, there in stemming, the stem might not be present in the dictionary. However, in lemmatization, the lemma that we obtain, the root form of the word that we obtain, it has to be present in the dictionary. So, for this we will be using again NLTK.stem module and WordNet Lemmatizer. This is the class that we will be using. So, we will define an instance of this class. So, let me run this, and we will have WNL. This is an instance of WordNet Lemmatizer class, as you can see. Now, what we will do, we will take few examples. So, we will use the lemmatize function to obtain lemma of a word here, and it uses word and it is part of a speech. So, for example, if we let us take the example of some nouns. So, second argument is typically used to indicate noun. So, that is as n in single quotes. You can see WNL dot lemmatize, and within parenthesis first argument is the word that we would like to lemmatize here, bikes, and comma and the part of a speech, it is a noun, it is a noun. So, let me run this. You can see bikes has become bike. Similarly, trains has become train. So, you can see part of a speech is also is required to be passed on here, because that will help in terms of identifying the root form of the word in the dictionary. Now, let us take example of a few verb. So, again in the second argument, instead of now we will indicate V to denote a verb here. So, writing will become write, typing will become type, and spoken will become speak, as you can see here. So, you can see how lemmatization is slightly different from stemming. Now, let us take another example, this time adjectives. So, better and A to indicate that this is an adjective. So, if I run this, you can see good, and hotter, we got hot. So, in this fashion you can see that how lemmatizer is working here. Now, let us move to the another aspect here, that is POS tagging. So, we just learned about that in lemmatization, that whenever we are lemmatizing a word or text or a particular token, we also indicate part of a speech. So, how do we tag all the tokens with their corresponding part of a speech? So, for that we have we will talk about this POS tagging aspect here. So, main part of a speech that are typically used in writing, and here also noun, verb, adjective, and adverb. So, it is important for us to label words with their POS tags, and typically pen tree bank notation is used for POS tagging, and most it contains the most widely used POS tag set. So, we will be using this NLTK's POS underscore tag function to perform part of a speech tagging. So, let us take an example. So, we will use tokenize underscore text function here, and we will pass on emma underscore sends. It will perform tokenization here, and then we will call this NLTK dot. So, NLTK dot POS underscore tag. So, first argument we need to pass on tokens there, and tag set also is something different tag sets are there, or you can just not specify this. So, universal is one example that can be used. So, NLTK, so in that code you can see that we first argument is token. So, we need to tokenize. For this I have written a function tokenize underscore text in the next section. So, here I will just also run another part of the code right now, so that we are able to access that this particular function here. So, I will run this part as well. and I will go back. We will come back to this part and discuss in detail, but because since I am using this function, so let me go back and use it here for Pos tagging. So if I run this and let us have a look at the tokens here. So you can see in the output here in the output 109 you can see Emma, noun, by, ADP, all those tokens they have been tagged with their corresponding part of a speech. So you can clearly see here. So you can see how first we tokenized the text and those tokens were passed in the Pos underscore tag function to perform the Pos tagging, and now you can see the output. So we would like to stop here, and in the next lecture we will move on to the some of the next aspect of transforming unstructured text. Thank you.